Hi everyone, I am Shivansh. I am a member of the MFP Club, and today we have a discussion on P-adic crystals. So, how many of you guys have already known about what they are? Correct? Okay, good. So I'll come to the basics, and then we'll continue to some cool facts of them. Okay. So basically, the idea here is, let's say we have some sum like 1 plus p square. So first let's talk about 10. Okay. So here it's 1 plus 10 squared. So what is this like as a number? It's 1, 1, 1, 1, 1. And infinite digits here. So what p-adic numbers do is, they allow us to have infinite digits to the left of our number. Okay. So in normal real numbers, what happens? If you have infinite digits here, then the number goes to infinity, right? And why is that? Because the modulus, like if you have some sequence 1, 11, 111, so on. Then in this sequence, the term you are adding each time, that's getting larger and larger. So that's why the sequence diverges. But what if instead of this, you define the definition of size differently? You said that the term you are adding here, it gets smaller each time. So what would happen then? This would get small, like this would converge to some number, actually. So in p-adic numbers, that's what we do. We define the modulus differently to get a new set of numbers. So I will definition here. What we do is, let's say the number is of the form 10 to the n. Then we define the size of this to be 1 by 10 to the n. So in this example, what happens here? Each time you are adding 10 to the k, and that k increases. So as you are adding more numbers to here, this gets smaller. Right? So that's why in this new definition, this number actually will converge to some number. We'll see what it is, but it will converge. So let's talk about why we can do this. What do we want the modulus to hold, basically? Also, one more thing, it's not of the form 10 to the n, let's say it's a times 10 to the n, where a belongs to 1 to 9. And then of the size is 1 by 10 to the n. It's just how we define it. Okay. So what do we want modulus to hold? So we want, let's say there's some modulus, mod of x, and we call this a mod of x, like with mod xp in p-adic. So here it will be mod x 10. So what we want is mod x more than equal to 0, because it's a modulus. It's like a measure of size, it should be positive. And mod x equal to 0 only if x equal to 0. Okay. Now, what are some more properties of modulus in real numbers? Let's list them now. Primary. Yeah, primary quality. So what we want is mod x plus pi less than equal to mod x plus mod by 10. Yeah. Anything else?
Mod of minus x is mod of plus x.
Yeah, mod x equals minus plus x. Mod x 10 equal minus x 10. One more basic one. What's mod xy?
Mod x.
Yeah. So we want that mod xy equal mod x mod y. So let's see if the definition satisfies these properties. Okay. So first of all, any number we have, if it's a times 10 to the n, to such negative numbers, let's include a equal to negative number. A belongs to minus 9, minus 10, 1, 2, 9. So the mod is 1 by 10 to the 8. Right.
Are we dealing with a equal to 0 separate?
Yes, we will. Okay. So this was the positive, right? And now let's look at 0. So for 0, any power of 10 you have, it will divide 0. So basically n can go to infinity here, like 10 to the 1, 10 to the 2, 10 cube. So as n goes to infinity here, what is equal to? 0. So for 0 we define the mod to be 0 separately. And mod of 0 equal to 0. And for non-zero number, basically it's the highest power of 10 divided the number, multiple of that. So let's look at the numbers. If you have mod of 870, what is this? This is that's a number.
Over here, left side, A belongs to, are we saying like A is an integer and it
Yes.
belongs to minus
Yes,
10?
it's integer.
Then how have we defined? We haven't really defined it for
It's
it.
basically wait, A is an integer, but it's not divided. A belongs to Z, comma 10 does not divide.
Oh,
Yeah.
so will it be 1 by 10?
Yes, 1 by 10. Basically, the highest power 10 dividing it, 1 upon that. So mod of 10 is 1 by 10. Mod 100 is 1 by 100. And now mod 870 is 87 times 10. Look at it this way. This is equal to mod of 87 times mod of 10, which will prove after this. This is 1 by 10, this is 1. So if 10 does not divide a number, the modulus of that is 1. And now as the number gets larger, like 10 to the n, 10 to the 100, that's 1 by 10 to the 100. So as the 10th power goes larger, the mod goes smaller. It's what we want to define different. Okay. Now let's prove this property. So what is mod x square? Let's say that our number is of the form a times 10 to the a1 into b times 10 to the b1. What's the mod of this? A and b are not by 10. Yeah. 1 upon 10 to the a1. And this is 1 upon 10 to the b1. And of course, if you multiply this becomes ab times 10 to the a1 of b1. And the mod of that is equal to 1 by 10 to the a1 of b1. Right? So does this hold? Yeah. Everyone clear on this?
Mod of 87, what's mod of 87?
1. Because 10 to the 0 is the highest power dividing itself. Yeah. So for any number not divisible by 10, the mod is 1. Basically, the mod here is the
Highest power
less 10 divides the number, the higher it is. Like, basically, if there's some number which is highly divisible by 10, its mod will be 2.
Say A is 2 and B is 5 in this case.
Then what is B?
Yeah.
Yeah.
And the product will have one extra power of 10.
Yes, I will. That's a good question. So in the topic of the talk, we said P-adic numbers. So what is P normally? It's a prime. So that is why this failed here. And I will give an example why we talk about P-adic numbers. So good catch. Next. Yeah. So I was coming to the cases, but in calculator we just go right now. So what happens in when P is not prime, our properties somehow they fail. Now in prime, what will happen if it's prime? Which is the same what will happen here? No. Yeah. So if we have a prime in P-adic numbers, it holds. I'll just continue on 10 for some more time, then we switch to P-adic numbers. To show the proofs. And one more thing, mod x plus 5 is equal to mod x plus mod y. So let's say that 10 to the a divides some number x and 10 to the b divides y. Okay. So then what will happen here? Just try to do this. And guys, don't hesitate to say it out. If you feel the doubt is or whatever, just ask them because it's a new topic. Everyone most people don't know it. Just ask whatever you feel like asking.
Here A is the highest power which can divide.
It's the highest power dividing. Okay, so what is the mod of this number? X.
1 by 10 power.
And what about y?
1 by 10 power.
So what will the mod of x? What will the mod of this be?
It depends upon if A and B are equal or
Minimum
not.
of A.
Yeah. So this mod of this is basically min of a, right?
If they are not,
Yeah.
if they are equal, then it can be different, right?
If they're equal, then
It can be different, na? For example, 10 raised to 5 into 10 raised to 99 minus 1 and 10 raised to 5 into 1.
10 raised to 5 into
1. इन दोनों का जब सम करोगे तो मैक्सिमम पावर 10 raised to 104 हो
Yeah,
जाएगा.
and that's less because it's higher power.
हाँ उससे but min a भी हमेशा नहीं होगा ना.
It will be less than equal to that.
हाँ it will be less than.
So what happens here is, when you add that, the power of 10 in x plus 5, it will be at least min of 80, right? You can have more because you can have something like 1 and 9 there, very right. But it will be at least min of 80. So what happens here is, x plus y, let's say without externality, that a is smaller. So 10 to the a will divide x plus y. Okay. So now this here is 1 by 10 to the a, and this is 1 by 10 to the b, right? And now here, since a satisfies this, we can say more than it, but at least a satisfies this. So this is strictly, not strictly, less than equal to 1 by 10 to the a. So if it's equal to 1 by 10 to the a, it's less than equal to this plus this. Right? And now what one could think here? Is this a stronger result? Like if y is not 0, then x plus y mod in 10 is equal to the max of them, not just this sum. So in this new modulus, we have a stronger result than just times the quantity. What we can say is mod of x plus y in 10 is less than equal to max of mod of x base 10 mod of y. Is this clear by words? So I think it's very cool that we have a better, like stronger quality here. And if y is 0, then it's equal to them. If x plus y is it's not 0, it will be the higher. And now about this one, mod is equal to minus x, that goes by definition typically. So basically, our new modulus which we defined, it works. It has all the properties which we wanted to satisfy. So it's not like you have some wrong thing like mod x y is like for P-adic prime at least. You don't have some random modulus, like it works. Okay. Okay, so the power is min, but the lower power has the maximum go. I'll give an example actually. So let's say you have 10 and 100. Okay. So what's mod of this? What about this? And now this sum is equal to 110. What's the mod of this?
1 by 10.
Yeah. So basically, this is the maximum one. It's equal to this term. So always it's less than equal to the maximum one here. So now what is shown is under this different modulus, we can write like this 1, 1, 1, 1, 1, so on. It's some number like if we define what is this, it's valid. And why is that? Okay, so first of all, look at normal, you have done normal effect, right? Have you done Cauchy sequences? Cauchy sequence and normal effect, haven't done? Okay, I'll go over anything. So we have some sequence. Let's say you have to write
The difference is
yeah, exactly.
Yeah.
I'll explain anyways. Let's say after root 2. So it's a irrational number, right? How do you write root 2 using rationals? How do you approach it?
The decimal representation.
Exactly. So root 2. So you write the 1.414 so on. So what you write this as is some sequence 1, 1.4, 1.41, so on, right? And this sequence, the difference between two terms, it gets lower and lower. So that's why this sequence converges to a value, and we call that value as root 2. So what are real numbers basically? Any real number, you can do this thing for it, right? So basically you have rational numbers, and then for any real number, they are caused by some sequence of rational numbers that converges to some value. And that is called completing the real numbers using rationals. So what we say is, under this normal modulus which you have in real numbers, completing the rational under that mod gives us reals. What that means is, if we have some sequence of rationals in which the difference between two terms under that mod gets smaller and smaller, that converges to some real number. Is that clear? It's a bit like wordy, but is it clear?
By mod, do we mean any modulus which satisfies those basic properties?
Yeah, so
This
right now forget about normal. Okay. And now let's do the same thing for the P-adic mod. So does it satisfy that property? This is 1 comma 1 comma 11 1 comma 11. So here, what's the difference between two terms? Yes, that's in a maybe we would have done it last year. It's a characteristic. So what is the difference between two terms? It's like 1, 0, 0, so on, right? And now what's the mod of this? Let's say it's equal to
1 upon that.
yeah. 1 upon that is there. So as we go along, the difference between two terms, it gets smaller and smaller, above the 0. Right? So under this new modulus of P-adic numbers, this number is defined and it converges to some value. Okay. And now let's see what the value is. So first of all, like earlier he said that we have to use times here because otherwise we don't have properties with it. Is that clear, Pi? We have to use times here. Okay. So let's switch to base 5 for now. 5 added numbers. So I write a number. You tell me what the number is. Let's say we have the number 4, 4, 4, 4, so on. Now what is this number actually? Let's try to find out. In 5.
Okay, so are we claiming that this is actually a natural number?
Yes.
Oh.
Not natural number, but a integer.
Ah.
Yeah, good. Just router can you tell everyone?
But adding 1 to just make this entirely clear.
Yeah. So what happens if you add 1 in base 5? What is answer 4 in base 5? Yeah. So 0 and then 1 carries. Now what is 4 again? 0 and then 1 carries. So what is this? We get 0, 0, 0, 0, so on.
It's kind of like minus.
Yeah, exactly. So this number plus 1, you get 0. And why do you get 0? Okay, first of all, it's for the real number. Then adding 1 here would not give 0 because let's stop it here. So 4, 4, 4, you stop it here. What you get is 0, 0, 0 and then a 1 here. Right? So for this number you get 1 without 0. Now if you stop it later, you get a bigger number. So for real numbers, you get a bigger number, so it doesn't hold. But for P-adic numbers, this 1, 0, 0, 0, 0, it gets smaller the more zeros there are. Right? So for P-adic, this converges to this plus 1 goes to 0. Got that or not? So what I'm saying is, if you have normal number, like the sequence 4, 44, 4, 4, 4 in base 5, adding 1 here gives 1, 0, 1, 0, 0, 1, 0, 0, 0, so on, right? In real numbers, this is not defined here, not convergent. It goes to infinity. But for P-adics, this same sequence, it will go to 0. Right? Because the power of this is 1 by 5 to the n. So this goes to 0 for 5 items. Right? So because of that, if we have 4, 4, 4, 4, 4 plus 1, plus 1, that equals 0. Okay. So now what is this bigger? It's the sum of x. Then x plus 1 equal to 0. So x is actually minus 1. So in P-adic, we have different numbers here. So we can write a minus here. But even without that, we can let the negative numbers use the P-adic. So 4, 4, 4, 4, so on is minus 1 here.
When we were writing the sequence 444, 444, was that in base 5?
Oh yeah.
Oh,
Everything is in base 5.
did we also implicitly use the property that when you add 1 to each term of the sequence, then the limit also, the 1 also gets added to the limit as well?
What do you mean?
We wrote 444, 444, blah, blah, blah.
Yeah.
We added 1 to each term, then said that this new sequence is convergent. So you can convergent to some L. So you can subtract 1 from the limit to get the limit of the original sequence.
So that's because in static numbers, addition and multiplication is well defined. And why that is this? And it's 3 months. So why that happens? So let's say you have some number and you add something to it. Some parameter. So what you can do is, you can add the number here, take the carries, put them here, add them here, and you can repeat this process. So what happens is, let's say you repeat it up to the finite time. You stop it here, okay. After that, it ignores the carries. So you get some number, call it k. Now let's say you increase the step. So what will happen is, it will reach this number to a higher point, and the carry which we ignored gets smaller. Why is that?
There is 1 by 10 to the power.
Yeah, because the carry has a higher power of 10 in it. So the carry gets smaller. So if you add some numbers and then stop adding at some finite point, that is some value get. If you increase the finite point, the value converges to the number more. So as you go along and stop at different points, it gets closer to the number. So basically in addition, you can, up to any finite point, you can estimate it. So that's why as you go to infinity, the addition gets addition. Because it converges. In normal numbers, if you add 1 here, like you have 4, 4, 4, 4, you add 1 here. If you stop it at some point, then that carry gets larger as you stop it later. Because like 1000 is more than 100. So that's why in normal real numbers, this addition is not verified for straight numbers. But for P-adic, since the carry gets smaller the further you go on, it's verified. Is that clear?
Shivansh, could you do a brief recap of what P-adic numbers are and what the mod is for people who came?
So what we have is in static numbers what we have is you have some number. We want that the higher the power of p divided by number, the smaller we claim it is. Okay. So let's say the number is let's say 5. So if the number is 1, 5, 25, so on, we want that this is more than this, so on, modulus size. So we define it to be, if the number is of the form a times 5 to the n, where 5 does not divide a, then the mod of this is equal to 1 by 5 to the n. And then what we showed was that this new modulus, it behaves similar to the normal modulus. Basically, it has a triangle equality, and mod x y equal to mod x mod y, and mod x is always non-negative, and mod x is only 0 when x is 0. We should know this. Fine? Okay.
When we find the mod of a number with respect to a particular p prime p, is it necessary that the number is written in the base p, or could it be decimal level?
You mean like 1.1?
I mean, like, when we say 4444444, that's written in base 5.
Yeah.
And we took the size, we took the modulus with respect to 5, right? So is it necessary that the base and the number written outside the modulus should be same?
You can convert it. If you have 4 base 10 mod of that, then convert it to base 5 and then find it.
So the method we are using
Like basically, if it's in a base p, then the mod is just 1 upon 10, 5 is the number of these after it. So it's easy to find. That was that. 4, 4, 4, right? So for mod 5, minus 1 is equal to 4, 4, 4, so on. Right. And now let's look at what we came here to see at the start. In my post, I said that 1 plus p prime is equal to 1 upon or minus p. So what is this number in the adic numbers? What is it? So it's just
One.
exactly. Okay. Let's for a test. Now, how will we find it?
X plus 1 is 0.
Is it here?
In binary.
In binary.
Minus
For the
1
present
by
P.
4.
P minus 1 by 4.
For 5 years. How will you?
Minus 1 by P minus 4.
Yeah.
So it is 1 upon 1 minus P1.
Oh, so 1 upon 1 minus.
Yeah, exactly. So let's say I'll just take on the side. So you multiply this with P minus 1. What do you get? You get P minus 1, P minus 1, P minus 1, so on. Right? X equal to X times P minus 1. Is this fine? And now you add 1 here. Plus 1. What do you get? Like you just saw, 4 from 4 goes to 0. Similarly here, 1 plus P minus 1 goes to 1 0. So 0 and 1 here. Then 0 and 1 here. And so on. So this equal to 0. So this is also equal to 0. So because of that, x times P minus 1 is equal to minus 1. So x is equal to 1 upon 1 minus P. So as you see here, this modulus, it might seem random, like we just put it and diagram. But actually if we define it this way, and we find like some properties here, it matches what we already know. So this, which goes to this for P less than 1. Yeah.
X into T minus 1 plus 1 is 0. Hence we obtained from using the property mod x is 0 if and only if x is 0. Right?
Yes.
This I understood, but how is, I think, how is subtraction defined? What is
Like
the
addition we defined, right?
Uh,
Same is subtraction also.
and I mean to ask how are negative numbers defined?
A negative number, this is like a normal real number. Like a normal real number. This is the P-adic number. This is a free representation. You can leave it what it is.
Like we said mod P is less than equal to 1, but over
Unless,
here, like P is of right.
so this is like I'm just saying for normal it works.
Oh, acha.
And now I see that even for this kind of number.
Oh,
Yeah. So normally it's true, right? We've all seen GP ka sum. But even for like in P-adic numbers, even for prime, this works. It's this fixed to carry numbers. Is that clear? So I think it's really cool that we just wrote this and we got this random sum by just using it.
For which P does a given x have a unique representation?
Yes. Because you can, like, let's say you have some 100. So take the mod P, then write that first. Subtract P and the other P, then take mod P times, mod P times. Like it's same as writing something in mod P. For some number. That's yes. Like you know binary now. You can write a number in binary. It's same method. Like for binary, instead of binary you have some mod P.
What does that relate to the P-adic representation?
Okay, basically like when we write some P-adic number, we are just like it's a normal number in base P, but we extend this to infinite as well. Take that. So for a normal number, it will be like normal, like 4 in base is equal to 4 only in P-adic numbers. Like if you have 10, it's equal to 2 times 5, that's 0, is equal to 20. And yeah, if I write it. Like it's normal case. Like you can have normal number, but you can also iterate it. It's not necessary.
Are you saying that the real number 1 over 1 minus P is represented as this?
Exactly. So, any doubt in the definition so far? Like, is the definition completely clear? Another question.
Bit of a doubt. Is this are the P-adic numbers a new number system?
Yes. Basically,
And to define a new number system, is it just an add-on to the existing number system?
I'll explain again.
Or what?
So basically, first you have rational numbers, right? let's say you have some natural numbers q. Now, to reveal what we did was in natural numbers, we take a sequence of some natural numbers and then close to some real number. So we completed q. From q we got answer using normal mod which we have. Okay. Now it should have this. If we complete q using P-adic mod, what we get is some new number system. It's called QP. Now this has some other new numbers. It might have like some other numbers in natural also, real also. It might have some random numbers. Like basically any sequence of P-adic numbers which converges to some number, that number belongs to QP. It's a new number system. And later I will show it has some very equal numbers which real numbers do not have. For example, 500 numbers make q of 5. It has some number which gives a iota. There's a number here which square is -5. I'll come to that later. It's pretty cool. Okay. So any more doubts in the definition and so on before we go to high and sharp?
The arithmetic operations like addition.
Yeah.
How would we do we need to redefine them or are we borrowing them from the definition?
We are merging them because it converges. Because for any addition, multiplication, and so on, why it works is we can find it out to find some finite part, right? Like we can stop the number at some A digits and B digits and find the sum multiplication matter. And as we increase A and B, the values we get will be closer to the actual value.
So you're saying in QP, the finite numbers we can deal with like normal addition,
Yes.
and the ones which go up to infinity from the left side, we can compute them like limit of a sum sort.
Exactly. And that's why it's well defined. Because the mod is written that way such that the higher goes here, whereas the mod is written.
Are you saying the set of real numbers is a proper subset of the set of all periodic number for a P?
Again. And that is because you can take, like, basically it's an aggregate binary. Like, let's say you have some real numbers, it's defined as 1.4.
Also, what do you do for decimals?
So, what?
For decimal numbers.
For decimal.
Like for 10.1, how do you write it in P?
10.1.
Let's say P is 5. You can take any example. I don't know.
So, it's a bit complicated, I'm not sure myself, but you basically like subtract some resistance. For example, if you have 1, 1, 1, 1, 1, so on, that's equal to 1 by 1 minus 3, right?
Yeah.
Now, similarly, if you change something there, you get some other new numbers, it's some fraction.
Yeah,
So, somehow using this fraction, you're able to write it.
okay.
I don't know, but like using manipulating this, you're able to write it. Like, let's say you have 2, 2, 2, 2, 2 in some way. That's equal to 2 columns. And also, for rational, what we allow is, we can write like 3, 3, so on, find some 1, 2, 3, so on. So what we allow is, for representing all numbers, we can write some finite decimal part here. Like in real, we can do infinite decimal part here. But for P-adic, we can go infinitely here and some finite part here. And that way we can write this as this plus 1 by P plus 2 by P square plus 3 by P. And using this, you can solve.
How is the mod defined in this case? Is the mod just one?
No, module will be PQ.
It will be?
PQ. The
Oh,
model
okay,
is
yeah.
like the high power here is e to the minus 3 divided by number. The model is PQ. Also, when you see this is, let's say this number is something. This times PQ is equal to 3 to 1.
Yeah, then we can use the mod property.
And we can use mod equal to mod size. So this times PQ ka mod is equal to this. And now this is equal to mod of this times PQ is equal to PQ. If it's this, like 3 different questions. Right? Yeah.
I understood why the representation of any natural number in P-adic is unique, but for negative rational, so there's 1 upon 1 minus P by P. Why is the representation of that also unique?
Let's say x is equal to 1 upon 1 minus 3. Now multiplication is defined, right? Multiplication is defined. So we can write 1 minus p times x is equal to 1. Now addition is defined, so that will define. So we can write that x minus xp is equal to 1. Okay. Actually, because of that, even this is correct. Because division also you can do the minus step. Division also you can divide by the final step and then sum over. So division directly is defined. So correct. Or also we can say that we need nothing other.
Uniqueness in what sense? Because we can write this as that 1 1 1 1 1.
Okay, I got this. So let's say it's a number x. Okay. So call it like this. A, B, C, D, so on. And I observe. Okay. Let's say x is some A, B, C, D, so on. Okay. Now times B, x will be 0, A, B, C, D, so on. Right? Okay. You should grab this. What do you grab? And the number is to be minus 1. Equal to 1. So A minus 0 is 1. So A is 1. Now B minus A is also 1. Right? Is there some mistake?
B minus C is 0.
Oh, no, B minus A is 0. Yeah. B minus A is equal to 0. So B equal to 1. Now B minus B is also 0. So C is also equal to 1. So that's fair.
1 cannot be written in any other way, right?
Yeah. One is just
Compare digit by digit.
yeah, exactly. So because structures are well defined, this minus is equal to this. Now we write this. Now a like each digit has to compare it. So by like this first thing has to be 1. Now because it's 1, next one should be 0, and so on.
If two numbers are digit wise different, is it necessary? If there exists a digit in the two numbers which is different, then is it necessary that the two numbers are different?
Yes.
That is, I think, we are implicitly using that.
Yes. Because they're different, it has some number here. So it has some positive number. Like let's say x not equal to 5. Okay. You take x minus 5. Now what's the mod of this? Because there's a different flux. This will have some digit is not 0. So mod x plus 5, like there's some key running it. So it's not equal to 0. Is this clear?
Shivansh,
Yeah.
what is the mod of 1 by 9?
Mod of
Base 10.
mod
1
of
by 9.
1 by 9 and base 10. Basically upper address 7 and then 3. Like
Is it like in decimal? Did you
Divide into 0.1.
you have to write it in base like the algorithm which I don't know, but you have to write it and see what happens. I'm not sure.
Can we do it in 10? Because
Yeah, can we do it in 10 because multiplication of the property bachayegi na? For these things we are using the
हाँ,
multiplication.
for
of
base
property.
5 will be 50. For base 5.
Then the 9x का लिख देंगे.
हाँ, you can do this way. Good. So let's say you have 1 by 9. So 1 by 9 is equal to some. Now 9 is equal to 1. Right? Now write like this and then this. Basically, let's say the mod of this is equal to this. Okay. So mod 9 is what? It's 1.
It's 1.
Right? Mod x is hence 1. Because mod x is 1. So it's 1. Actually, this also let us say guys. Let's say you have some number which is p to the n times a by b, where p does not divide both a and b. Then the mod of this is 1. Because we can take the mod property of mod s equal to mod s mod y. This is equal to mod of p to the n times mod of a times mod of 1 by b. And this is equal to 1. This equals 1. Hence it's a solution. Is this clear? Right? Yes. So now I write some number and it should happen to that. So look at the number which is 2, 1, 2, 1, 3, 4, 2, 3, and 4. Okay. This is some number. It's in periodic base type. Okay. Now let's weigh this number. Okay. So times 2, 1, 2, 1, 2. So what 2 times 2? Now this will be 2 times 1 plus 2 times 1 times the 10 of 5. So that's also 4. And after it is like the rough stuff, but basically what you get is you get this to be 4, 4, 4, 4, 9. Okay. Yeah. So what is this? Some x times some x gives this. What does that mean? Yeah, exactly. So that means that x squared plus 1 equal to 0. Right. So basically this number which you wrote using only real numbers. It's like kind of like a common number. Like it's not exactly iota, but it's kind of like iota. Like x squared for this number is minus 1. Which is I think really like because real numbers using P-adics, we made a number which square is minus 1.
What's stopping us from writing x equals I? Just
Because like we haven't defined something like it. Like let's look at modulo base p. For that also you have some like a times b equal to minus 1 modulo. But a and b is not like like 2 base p or 2 base 5 may 2 square equal to minus 1 mod 5. But 2 is not, so it's not exactly iota, but it behaves like iota. Like it square is minus 1.
I didn't get the proof of that thing. Ki if two have different representations, then they are different. वो एक बार आप और
Okay, I'll explain it. So let's say you have some x and y. Okay, x are equal to y. Now send x minus y. Okay. They are different.
Yeah.
So there will be some digit, right? So now take the mod. Since there's a digit, there's some power of 3 dividing this. It's not equal to 0.
But फिर इस logic से can't I say that decimal में भी hold करेगा? But I know in decimal 1 and 0.9.
Because the thing in decimal is you can have infinite numbers after this.
हाँ तो इसमें I can have before also right?
हाँ.
So इसमें भी there might be some similarities.
but कोई
No, but
finite
it
point
doesn't
पे ही 1 आ जाएगा ना? Wherever it differs, वहाँ पे 1 आ जाएगा and the rest will be 0.
अच्छा हाँ.
So
Did you really understand this number? We have written some dot each other.
वो ladder मतलब बेटा perfect. Direction we कैसा है?
There is construction for all the digits. Can we find
Yeah,
the
I
general?
okay. So what happens is, look at these numbers. 2 to the 5 to the 1. 2 to the 5 to the 2. 2 to the 5 to the 3. So, okay. Now what happens here is, look at this. Let's say it converges. Like there is a zero converges. So the value in 5. Okay. So what will happen is, let's say 2 to the 5 to the n goes to infinity equal to x. So now 2 to the 5 to the n is equal to 2 to the 7 to the n. Working for some x. Okay. Like after the infinite limit, this should work. If it converges. Okay. So that means that x is equal to x to the 5. Is this clear, right? Okay. So now, since the division is defined, you can divide by x and you can factorize it. So what we get is x squared minus 1 times x squared plus 1 is equal to 0 for this sequence. If I come like this, right? And now x is not 1, it's not minus 1. So x squared plus 1 is 0. Yes, division because it's basic.
No, after this, the conclusion that x is your 1 minus 1.
Because you can divide by 10. In base 10, it doesn't work. We can't divide. But for base 5, it works. So this sequence, if it converges, we get x plus 1 equal to 0 for it. And actually, if you write the terms out, you see that this, when you like increase n, you get this number. The more you increase n, the more it matches this. So that's how we find the number. Like, that is how we find the number here. We see the sequence, we find its terms, it matches this. So like 2 to the 5 to the 100, the first two numbers will be this.
we'll also have to argue that this is not equal to 0 before dividing, right?
Ha, because x is not equal to 1. And x is equal to -1.
It doesn't matter whether we take 2 as the base or the base doesn't matter, right?
For this,
2 power 5 power 1 we are writing 2 power 5 power 2, the 2 doesn't matter.
basically what we saw like in like
So basically
What?
I'm asking whether 2 power 5 power 100 and 3 power 5 power 100 would have the same.
basically when people were solving this, what they saw was that for this value it converges. Like maybe for 3 to the 5 to the 1 it does not converge.
Doesn't matter.
It's possible. Like it's not a formal proof, but for 2 they wrote this and people saw that it converges to this value. Like it's a experimental kind.
How do you know this converges?
Like we couldn't. I don't know the proof, but basically.
Oh, so in general to prove convergence will be like try to use like Cauchy's theorem, like that any two arbitrary terms get like arbitrary.
Yes.
That what.
That's actually it. So what we can do here is we can like look at the power by dividing it and then
Achha,
we can
all of them have the like.
like I think we can use Fermat's theorem for something. Like we can write the difference values to the 5 to the n plus 1 minus to the 5 to the n, and you can somehow prove that the 5 to the something divided, and that gets solved. Like if we can prove this, we can get what we want.
Yeah.
Is that clear what I just said?
No, what was the last part?
Okay, so basically, we want to prove it converges, right? So if it converges, the difference of two terms of the 0. So this will 0. And we can use some number here, we can use 2.
VP of
But we always have to again and again prove that increasing sequences converge. Isn't it a general theorem in p-adic numbers, like it seems to be?
No, like you can
If
have,
it's an increasing sequence, it should converge because
you can have this 1, 2, 6, 7, add 5 to 3, like 11, 12, so on. This goes to 1, 2, 1, 2, 1.
So this way first we prove the limit exists, then because it exists we can write that x equal to x.
Yeah, exactly. And I think for what is it like for 3, if it does converge, you can maybe get -i. I'm not sure, it might be 2. Like this has 2 numbers, right? And +i. Maybe you might be with the other numbers. It's possible.
Alright, so did
Why
you
do
say
it's maybe I? Why isn't it just? It is iota, right?
It's not exactly
The representation of iota in
it's a
p-adic.
real, it's a real, it's not a complex real. Like for real, it's complex, but for p-adic, you haven't tried. Like for modulus, you have 2 square is equal to -1 mod size. But 2 is not iota in mod size. And one more way to find this number is just multiply C. So let's say you have two numbers, this, so on. Yeah, A, B, so on, and this equal to 4, 4, 4. So if A square equal to 4, then A can only be 2. Or A can be 3 actually. Yeah, A can be 2 or 3. And now if it's 2, let's say. Now you can find that what is 2 times B plus 2 times C becomes 4. You get B1, so on. So this way continue and then you get the number. And also, like I just said, you have iota and minus iota kind of. So if you take 3, you get the
What differentiates this number? Just now you just said that x square plus 1 equals 0 can be satisfied by 2 also for base 5.
for base 5, yeah.
Yeah, so what
But
differentiates?
not for like for p-adic numbers, 2 square plus 1 is equal to 1. It's not base 5.
Oh, yes, sir.
It is. And one more cool thing, if you have a number, like what is the number here? 2, 1, 2, 3, 4, so. How do you take it negative?
Just 5's complement add.
Exactly. Yeah, so let's say if you add something here to get 4, 4, 4, so on, then this number plus 1, reduce it, right? So you subtract 4 from 4 numbers. So you get 2, 3, 1, 2, 3, 1, 1. And this number plus 1 is equal to 3, 3, 2, 1, so on. So it's a negative with this number. So if this square is minus 1, this square also minus 1. And as is always, it's until 3. So, and the first bit of 3 of 2, we get a minus 1. And maybe probably also 3 to the factor line will go to this. I get it. Might be good to turn the calculator and see.
Wait, so by this we could get 2x such that x square is minus 1, right?
Yeah. Even we have thought
Yeah.
it's like this.
So you argued last time that the 2 power 5 power r series converges to one of the.
Yes.
Okay.
And maybe 3 to the r converts to another. And now, okay, so far it's clear. Is it interesting enough for okay. Now I'll go over this is some like we did something. What is the use of this? You can use it somewhere. So I'll go over a question and number 3 we can use this one. Okay. So let's say you have a solution of x square plus x to the 4 plus x to the 8 is equal to y square. Okay. X square into this. Go to this. Okay. So now we have like this right. Okay. What we do here is we consider x to be some p-adic number. Okay. So let's say x is equal to some a plus b times e to the 1 plus 3 times c square, so on. Okay. Now what we do here is first we find a. Okay. And why do we try to remember this? Because if something square is like basically for 3 numbers, you can only have 0 or 1 in the square. You can't have x equal to 2 multiplied. You know that? Yes. So that's why taking this limits our choices of y based on x. So let's say first we took this mod 3. So x square mod 3 is a square plus a to the 4 plus a to the 8 is equal to some b square root. Okay. A can be 0, 1 or 2. If we take it to be 0, we get 0 here. For it equal to 1 is 3 equal to a bar. So it has to be reversed. Because if something square is 0.3, and for a equal to 2, we have 4 plus 16 plus 275.
Is it given as x and y integer?
It is. But actually, what happens is that
So wait, where is the P-adic here? It's just taking mod 3.
because what will happen is
Modular.
yeah, we get that it goes in like we can't cover it. I'll just share. What we get is we get x to be 1 plus. We get to be this. Where was I? How it is not here. A square plus so if a equal to 1 mod 3, then this is equal to 0 mod 3. If a is equal to 2 mod 3, also equal to 0 mod 3. And if a is equal to 0 mod 3, also this is 0 mod 3. This is 0 mod 3. Now let's look at the next one. If you have so got the exact answer to this. May I make a try this? You have to try this. Okay, just try once more. So we don't immediately solve this, but we like have some solutions.
Even if we did something using P-adic numbers, what's the guarantee that the solution we find in P-adic numbers corresponds to a solution in like a normal number?
We verify.
No, just that we found all the solutions.
No, sir, bunch of. Not all.
If we disprove a solution in p-adic numbers, do we disprove a solution in real?
That is
Yeah.
Is there a bijection basically? Because we're treating it as if P-adic numbers is just another way to write numbers. But
So R is a
the whole
proper
basis is
subset of
different,
p-adic,
right?
right? So if a solution doesn't exist in p-adic, then no solution can exist in real. But
I am not sure. I will just watch.
Shivansh, if we find a solution in p-adic, we cannot be sure if it is a solution in R. But if we don't find, then we're sure that no solution exists.
No, this is just, we are not finding solutions. We are constructing one possible solution.
Yeah, but we have to say that this exists in R also.
Yeah.
We cannot just say.
If we don't find them, we can say
Yeah,
that.
if we don't find, then it doesn't.
Because then you can't have something more. Up to some finite point, you have to have it.
So does the solution to this exist?
Yes, not in individual. If you know you have. Otherwise, what you have is half. Half for rational.
Oh, we are looking for integer solutions or rational solutions?
We would find this and we would rational. So what, I'll just start or get them? Where are they? Okay, I'll start. So let's say we got that this y has a rational view, right? And now let's say we took the first step to be y. X is equal to something y. Okay. Now let's look at this mod 9. So x is equal to 3k plus 1. So 3k plus 1 square plus 3k plus 1 to the 4 plus 3k plus 1 to the 8 is equal to y. Y is also mod 0. So some 9
you said x ka last digit is 1, that is like assuming ki it's not given.
it's some assumption. We are not proving some solution. We are making some solution. So like arbitrarily we just chose it to be 1.
Shivansh, how did we go from x equals dash 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 1 to 3k plus 1?
X is equal to this times 3 plus 1, right?
What?
If the rational is 1,
Yeah.
then x, this number is equal to 3.
Okay. Yeah.
So what we showed was that this y has to be 0. So we can just take it as okay. And now if we take what 9, then you expand this and you get to expand this for flow as well.
No, just write it.
What is the result?
The result here is that you get that, then this also 1. And then if you keep on assuming, what you can get is that 1, 1, 1, 1, 1, 1, so on, satisfies this. So using P-adics, you can go on, you apply induction actually, and you get that 1, 1, 1, 1 satisfies this. And now what is x equal to 1, 1, 1, 1? What is this? Minus 1. Yeah. So now x equal to minus 1.
What's that written on the RHS? Is that 3k whole square?
Yeah, because we got that y 0 1. So now what is this? It's half square plus half to the 4 plus half to the 8. So now this is 64 by 56 plus 16 by 56 plus 1 by 56 equal to 81 by 56, which is equal to 9 by 16 square. So what we do? We took some, like phase 3, we found the solution in current numbers, and that solution gave us a like rational solution. It's pretty good. Because we were trying to make it a solution. Integer bit in the other number. But it gave us a
What was the problem statement for this exactly?
just find a solution.
Find a what, rational or
Integer. So
integer?
we tried to find the solution. We tried to find it. Matlab we tried it.
Okay.
But we ended up with
Using just integers, we came up with a
yeah, exactly.
So are we arguing there is no integer solution, or
No,
are,
this is a solution, not the only.
no? But are we saying there is no integer solution?
We are not saying that.
Okay.
If there is an integer solution, it's 0.
Like 0, 0, 0 is enough. Like here we just took this way one, na? Like we can take 0 also, we can take 2 also.
So we just found a cool solution trying to look for an integer
Yeah,
solution.
exactly.
Okay.
It's not a only, it's just a.
It was because the properties of addition
Yeah, those are mine.
multiplication are considered.
So what do you think was the coolest part of it?
Last part, those are not very clear.
Could you give an idea of how we got like k is also 3k plus 1? I mean 3m plus 1 from this? Yeah.
We just assume that we shot that.
No.
We can take anything here, and this is just not.
No, I'm saying from that equation we got that k has to be 3m plus 1, right? For this to
So
hold.
we got that for
3m
k
plus one is
equal to
consistent.
0, 1 or 2. Or for all of those, this has to be not 0. 0 not.
No, I'm saying like in the later part of the solution.
So this,
Yeah,
we
this.
expand this out and then we
And then we
expand this. We take the 8 power here, we remove the term.
and what do we get? Like k is 3m plus 1, right?
Yeah, we get that, we take the mod 9 here,
Okay.
and we get that mod 9, this has to be
1.
So k has to be 3m plus 1 or 3m plus 1 satisfies it more?
for the first step it has to be, for the first satisfied.
Satisfies for the second step it has to be.
Yeah, exactly. I did a video actually to prove this, I forgot the entire proof, it's very long, but I can.
So if the last digit is 1, then all the digits.
Yeah, I think it.
Could you send the video on the group?
I had a doubt in that x square plus 1 is equal to 0. Can it have more than 2 solutions? If I am seeing p-adic numbers mod 7, say.
Okay, I'll see. So for mod 5, we got a solution, right? So here what is this? So let's say we want to find solution mod 2. I'll explain it. So let's say we want to find x squared is equal to x plus 1 equal to 0 into what is it? Can we find it? Just write some number times itself is equal to 1, 1, 1, 1, 1, 1. Just write it. Because you just can't take it to the 0 or 1 or
But if we look mod 7, then like 3 raised to 7 raised to n, then 5 raised to
even though mod 7 you have to do it. If you write this, you take the cases, you get a bunch. So what? There's a proof of this thing from a data number theory. But what actually happens is, if you have some p-adic numbers, then there is some number such as x squared plus 1 equal to 0, if P is equal to 1 mod of P. I won't prove this, but it has a proof. You take some comment. It takes some percentage relatives of it. So for 2 you want it, for 7 you can't do it. But for 11 you can't do it. You can do it for 13.
That means 3 raised to 7 raised to n is not convergent.
Yes. Like what you do is maybe you can take something like e to the 7 to the n plus 1 minus 2 7 to the n and then show that 7 is just some height out of the
So now if we apply the lifting the exponent lemma here, it will be like 3, this can be written as 3 raised to 7 times 7 raised to n. So it will be a B3 of 3 raised to 7 minus 3. That will be more greater than equal to 1 because 3 raised to 7 is converted to 3 mod. And plus B3 of 3 raised to 7 raised to n. That will be n will greater than equal to n plus 1. So it is increasing. So the modulus will decrease. That means
increasing doesn't matter. For it to decrease, like the power is not to be higher, not just the number. For this to decrease, the power of 7 divided has to the power of 7 divided has to
yeah, it's going up.
Until even then, you can like if you have this number, you get that x plus 7 equal to x.
What happens?
So you get x plus 6 equal to that. So that can be true for omega and for I. It is true, but it can be true for other numbers.
X equals minus.
So maybe this will give some number which is not I, but it's kind of.
Yeah, so if you square that, what would it be? If you square this, but if I square this, that algorithm not of multiplication. And if I just multiply this to itself,
No, I think that might have to be unsafe.
how?
Then x square is x square mod P is P minus.
Okay. I think. For the first part.
Okay. Okay, so this is just one.
Anything I explain again? Any doubt?
I think it comes
Yeah,
to be
converges to one. Last year, I didn't go.
yeah, I don't know.
Who took
Yes.
So we can ask out.
Guys, the main part is done. You can answer it.
Could you clarify the part where is there a bisection between R number system and this P-adic numbers? Solving equations in this number system, would it be beneficial? Like, would it be exhaustive?
Bisection is definitely not there because you can have numbers like numbers like bisection is. I think it's a integral relation.
When you say integers, what are we doing? Integers
So
of R number?
it is real numbers. Index to integers.
Integers of number injects to integers here. And there are some integers. When we say integers here, what do you mean? Just numbers which don't have decimal point.
These all limits are equal to x. Because this positive number you can have a correct representation. For negative you can take the formula. Subtract from P by
Going off of what he's saying, there's a proof which exists, like you can get a unique p-adic number for a real number, right? So how do you argue that? How does one prove that?
So for I think I'm not sure, but for rationals I think we prove it.
Yeah,
And then using completeness we prove it for
using
completeness. Like
Completeness
the
of
sequence,
what?
the logic is fitted.
Oh.
Like, maybe a try.
Okay.
Like the great concept is that are we sure that number will work? Because if we only find the finite number digits, we're not sure that that number will satisfy my equation. We're not sure if it will satisfy. So in fact, we're sure it will work.
We are not sure. We look at this point. I think
And is it every real number with just the digits before the decimal place and like what? We need both.
after very fine. Before,
And what are the numbers which neither repeat or like, they are like pi is an irrational number, it has all numbers not repeating and neither terminating. So what do P-adic numbers which don't form a sequence? Like, there it was repeating 1 1 1 1, so we were able to figure out what. But if it is complicated, yeah.
So for P-adic numbers, there's sometimes there's no error. Like for this iota molecule, like there's no error. So P-adic numbers are basically more than error.
So this kind of iota will neither be repeating nor be terminating.
Is there a p-adic number with finite places which is irrational? Is that possible?
Because you can have.
Okay, yeah. That's not. Sorry.
So I have found a result as one raised एक result ऐसा है 1 raised to p raised to n 2 raised to p raised to n so until p minus 1 raised to p raised to n are
Or what?
are n through p minus 1 roots of 1 in period. Oh, 3 into p raised to n so on.
They just take an order and like you can do the same procedure for
Okay, so
them.
like
So
for
order them will come in
5 it's
expect.
हाँ 5 वाला तो उसका मतलब ऐसा है कि like for example any वाले को आप p minus 1 की power ले लो minus 1 मतलब कोई भी x ले लो तो x raised to p minus 1 का अगर आप not consider करोगे that tends to 0 by Euler's theorem.
But how do you prove they are distinct? Or is that
No, like for 5 you only have. Wait, what is the mixed probability? M minus 1.
p minus
P minus 1.
because every मतलब every number is to p minus 1 is pending.
1. Okay, so we are saying that for 5, 4 to the p to the n, then 4 to the 4.
What are we saying exactly?
Not
P to the n, 2 to the n, same.
2 part.
I'm just saying it will be a solution of
You
x
can
is
do
to 4
that
equal.
spread. You can do the spread.
I don't be different.
And then like see first
It won't be distinct.
for 5 and
Because,
2 are
like you
5
said,
are
for 5 you have
equation, no?
2 to the 5 to the n,
5 to
right?
1
And 1 to the 5 to the n is
plus
1.
p.
Like 1, this is what I say, let's say 3 and 1 minus 1.
Any of
Okay.
the numbers
So we want that for particular
P
line.
power 5 power.
But for 4, you can have 4 to the p to the n is equal to 2 to the p to the 2.
part,
Because for 4 to the p to the n,
then sum
it's equal to 2 to
then
the
this will become
square. P to the 2n.
this is from this.
no, it was
But then
2 into
the
p.
proof is close.
2 into 2 to the p. Then directly put it. Right actually.
We know right 4 4 4 4 goes to minus 1.
Yeah. But I'll let you factor it out. Let's just try it.
उससे तो grow हो जाएगा p
Minus 1 roots of it. Again, so it's going to be probably mistake.
I took the word.
उसको p minus 1 को power raise करते हैं by Euler's theorem that is tending to 5 here.
minus 1.
5 of p
Oh, calculator can't handle it. Calculator can't handle it. We can't.
Could you actually like
raise it to
write
the power of p
what
minus
he was saying?
so it is
When
x
we raise
raised
it
to
to
p minus 1 into p raised to n.